Hey class, today we're going to talk about a cool subject. We're going to talk about the intersection of central carbon metabolism and dieting, how the ketogenic diet works, why microbes can live on fats and we can't. So to start off with, the take-home message that we're going to learn today is that there's no way for us as humans or other eukaryotes to convert acetyl-CoA into glucose in a net fashion. The reason for this is that this reaction here, pyruvate dehydrogenase, is an irreversible step. And we're going to go through this today and how other organisms deal with this problem. But we have no net way of taking acetyl-CoA or any other 2-carbon unit and converting it into a 3-carbon unit that can go into glycolysis. Talk about this some today. So to start off with, let's just remind ourselves here that glucose undergoes this glycolysis ultimately to make pyruvate, and pyruvate is the carbon that feeds into the TCA cycle. So that becomes an acetyl-CoA, and in the process we lose a carbon dioxide, and we ultimately get this NADH. So this acetyl-CoA can also be made though from the breakdown of fatty acids, and it can also come from acetate directly, and there are also many other amino acids that can be degraded into acetyl-CoA. So there are multiple pools of it. But now I want to ask you this question: why can't we take this acetyl-CoA and turn it back into glucose? Let's talk a little bit about that biochemistry here. So the first thing that you might think about is Pepsi K, or this enzyme that we use in gluconeogenesis. We do have a mechanism that takes oxaloacetate and converts it into phosphatidylpyruvate, and we use that for gluconeogenesis, right? This is one of the first steps that we have in gluconeogenesis. But why then can't we convert an acetyl-CoA in? Why can't it just come in here and we can combine it here? So the reason for that is, as acetyl-CoA goes in, if we're going to be adding it to the TCA cycle, as it moves around the TCA cycle, we lose a carbon dioxide here and a carbon dioxide here. So by the time we get back to oxaloacetate, the same amount of carbon has been lost through the TCA cycle as has been added in through the acetyl-CoA. So it doesn't matter how many acetyl-CoAs you add in, you'll always be losing the same amount of carbon that you're bringing them in if you bring them in this oxidative form. So Pepsi K cannot in net form move carbon from acetyl-CoA into oxaloacetate, not using the biochemistry that we have. Now, as it turns out, we aren't the only organism on Earth, and there are other creatures that have evolved some really cool solutions to this problem. And the solution that the microbes use is called the glyoxylate shunt. So plants, bacteria, fungi can have this pathway, but we don't. And this is really essential for plants and bacteria, because if you're going to live off of, fat sources, or you have a limited supply of nutrients, then being able to make the most out of fats is really critical for your survival. So the key to this pathway working is an enzyme called isocitrate lyase. Isocitrate lyase takes isocitrate, which, as you recall, is this intermediate in the TCA cycle, and it cuts it in half into glyoxylate and to a succinate. Okay, and then that enzyme, in combination with another enzyme called malate synthase, will take that glyoxylate and another acetyl-CoA and ultimately make malate. Okay, so let's look at this from a net chemistry sort of perspective. So if we look at this guy here, we'll see that this pathway then loses or uses an acetyl-CoA, or I'm sorry, an oxaloacetate. An oxaloacetate and acetyl-CoA get combined. This is our standard citrate synthase reaction. Goes all the way around to isocitrate, and then isocitrate lyase then will allow us to regenerate a succinate, take a second acetyl-CoA, combine it with oxaloacetate, or with the glyoxylate to make an oxaloacetate. So the nice thing about this thing is it regenerates oxaloacetate, right? So the incoming carbon that we have at the front side of the equation is balanced with its equivalent carbon coming out. And in addition, we have this net production of succinate here, right? So we are adding carbon in net form. to the cycle, and that allows us to pull carbon out and ultimately drive the gluconeogenesis via the Pepsi-K. So overall, we have an exchange of oxaloacetate to form, the overall net effect is that we have the production of a new oxaloacetate that can enter gluconeogenesis. This pathway requires isocitrate lyase, and we don't have that enzyme. So the glyoxylate shunt is regulated via the availability of both energy and reducing equivalents here. So as ATP levels and NADH levels are high, they suppress isocitrate dehydrogenase, and when they're low, they activate isocitrate dehydrogenase. These are two of the master regulators here. So overall, what have we learned? The glyoxylate shunt is a cool way that microbes have that allows them to eat fat, eat ketogenic proteins or amino acids, and convert it net into glucose, something that we can't do.